Hello, and welcome to the video presentation of Project 26012, the dynamically scaled flight and wind tunnel model of a modular UAV for scientific flight experiments.
Hello, my name is Zachary Yang, and I'm the project team lead.
My name is Ben Columbia, and I'm the procurement lead.
I'm Kyle Fairbanks, and I'm the materials lead.
My name is Diego Fernandez, and I'm the CFD lead.
I'm Kira Drovati, I'm the electrical lead.
I am Jason Voris, and I am the CAD lead.
The main goal of this project is to build and fly an approximately 1/3 scale model of last year's senior design team, number 25059, shown here on the left. They built a large payload aircraft that could study the effects of various sweep angles and geometries with a high degree of modularity. However, that aircraft, designated Swan, cost in excess of $11,000, and the risk of crashing on the first flight was too high. Our team, 26012, designed, built, and flew a scaled-down model to determine the feasibility of the Swan as a flight testbed vehicle. The process of manufacturing our aircraft began with the wax molds. We utilized a computer-aided manufacturing software and a CNC router in order to create molds with a complex geometry of our nose cone, wings, and T-tail. Next, we used those molds to hand lay up carbon fiber structures for the wings and tail, and fiberglass structures for the nose cone and tail cone. This arduous process involved many hours of learning how to optimize layups, sanding excess material to form, and bonding composite structures together.
3D printing let us rapidly design, test, and iterate custom parts that would have been slower and more expensive to machine conventionally. We used PLA for quick non-structural parts and jigs, nylon PA 612 CF15 for high-strength, lightweight structural components, and aluminum magnesium SLM for the wing box, where we needed high strength without the delamination tendencies seen in nylon CF. This gave us a fast, material-specific workflow that allowed us to quickly adapt and refine our designs as needed.
Our first set of requirements are our dynamic scaling requirements. We must have a geometrically scaled aircraft to Swan. We will determine the moments of inertia and weight, which shall not exceed 6.33 pounds. We shall predict the moments of inertia and weight scaled for Swan. We shall sustain a wing loading of 5 Gs, and also shall have an n-scaled linear acceleration and a matched road number. Going to our next set here, we have modularity. We shall have a variable sweep angle from 15 to 55 degrees. We shall have a modular wing attachment point, landing gear, and engine mount attachment points, and a modular tail volume. The UAV shall be piloted via remote control and should have autopilot capabilities. It will be flight tested to identify any control instability issues that Swan will encounter in flight, and should collect in-flight data such as altitude or velocity, and it shall not exceed 100 miles per hour and 400 feet in altitude.
Here is the CAD model of our dynamically scaled aircraft. This aircraft was scaled from last year's model using a scale factor of about 0.353. As you can see, the aircraft is modular as the landing gear, wings, tail, and motors can be adjusted using the hole patterns as shown. Here is the exploded view of our aircraft. Take note of each individual subassembly and part that is used to create this model, as it is replicative of our manufacturing process.
This is the layout of our electronic system. To start, this is our RC transmitter with which we control our aircraft. These are twin 50mm electric ducted fans, each of them powered by a 3300 kilovolt three-phase motor. At 100% throttle, each fan can produce about 5 newtons of thrust. Each motor is controlled by an electronic speed controller, or ESC. Each ESC draws current from our battery and powers its respective motor. Each ESC also separately powers our RC receiver, which sends PWM signals back to each ESC. The RC receiver goes in the nose cone, and we also have a separate receiver that goes in the tail cone to provide more RF coverage. Each of our 7 control surfaces is assigned to a separate port on the RC receiver. On the RC transmitter, each of the 7 control surfaces is assigned a channel. They include throttle, left aileron, right aileron, left elevator, right elevator, rudder, and nose gear.
For our requirements verification, we performed 2 tests, the wing loading and the static thrust test. For the wing loading test, we clamped our wing upside down to a table and slowly loaded sandbags in a quasi-elliptical loading distribution until the total weight reached 5 Gs. For the static thrust test, we built a custom test rig that would hold the electrically ducted fans. And as we throttled up the EDFs, the scale underneath the test rig would measure the force exerted.
Okay, so here is our X-Flyer 5 aircraft. It is a quick simulation tool that we can use to determine key aircraft properties. For example, we are able to determine if our configuration is going to be stable in different route locus plots, as well as different aircraft polars. This gives us the ability to quickly test configurations and different sweep angles to determine if what we're building is viable.
For the wing loading test, we incrementally loaded the wings elliptically using sandbag weights. We loaded up until 5 Gs of force, or 23.4 pound force, based on the UAV weight of 4.675 pounds. The result was a pass due to the failure of the wing occurring at 31.6 pounds of force, which is greater than the 5 Gs of force that we were expecting. We conducted static thrust tests on both of the electro-duct fan motors to ensure that they were both producing the same amount of thrust. This resulted in us finding that one of them was underpowered, which was then corrected in the electronics layout. The moment of inertia inspection resulted in the roll, pitch, and yaw modes of the aircraft being found to be stable. The above video shows how the test was conducted. Here are our upcoming deliverables. First, we will need to complete the design day poster by April 24th to ensure that it is ready by design day on May 4th. Next, we need to manufacture a second aircraft by May 4th. As well as we would need to finish our final report, which includes design suggestions for the Swan aircraft by May 5th, as well as finalizing all CAD and document testing and analysis. Our first flight test was conducted on March 11th at the Tucson Radio Control Club. Alex Feist was our pilot, and we were able to confirm the UAV's ability to taxi, accelerate, and take off, as well as identifying dynamic instability in the aircraft. Our second flight test was conducted on April 11th at the Catalina Radio Control Modular's RC airfield. Tyler Cook was our pilot, and we demonstrated a solution for the Dutch roll instability seen in the first flight test. We also identified elevator deflection rate issues. The third flight test was conducted on April 14th at the Catalina Radio Control Modular's RC airfield. Tyler Cook was our pilot, and we will let the video speak for itself. We have now demonstrated a successful flight test of the UAV.
Two of the main surprises that we had were RF signal loss caused by the carbon fiber and dynamic lateral instabilities. However, we were able to correct these issues by creative antenna placements and by adding large wingtips, which resulted in a successful third flight test for us.
Safety is a core part of our project. In the composites lab, we work with carbon fiber, fiberglass, and epoxy resins, so all members wear a particulate and organic vapor respirator, safety glasses, and full PPE. We use wet cutting and vacuum-assisted methods to minimize hazardous dust, and everyone completes composite lab safety training before touching any equipment. For flight testing, we fly exclusively at designated RC airfields with an AMA-certified pilot, a dedicated spotter and pre-flight checklist, and no one is permitted on the airfield while the aircraft is active.
We would like to end by saying thank you to all the people and organizations listed in our acknowledgments section. This now concludes our video presentation.